So hello, thank you for taking the time to watch my presentation. My name is Sang-Hoon Kim, and I'd like to present this collaboration work called DEX. As you may already know, the data volume in the world has been growing exponentially. Many surveys expect the growth will be continue and even increased further due to the emerging data-intensive applications for such as machine learning, artificial intelligence, and Internet of Things. In this trend, many machine learning and data analytics want to get the result within a short latency. To satisfy the requirement, there has been increasing demand for high-performance scale-up machines with extreme processing power and memory capacity. However, building such a scale-up machine becomes challenging and expensive due to the end of Moore's law and increasing complexity of processor interconnects. In the meantime, the network technologies have evolved very fast. Modern network technologies such as InfiniBand, Omnipath, Gen-G, and recently proposed CXL provide a high bandwidth at a low latency. So in fact, these network technologies are blurring machine boundaries and make it cheap to utilize resources from remote hosts. This trend looks very same to what was happening in the past. When we faced a performance war for a single process in the early 2000s, we could move forward to multi-process error by leveraging high-speed process interconnects. Now we can do the similar approaches by leveraging those high-performance network technologies to bind multiple machines and use them like a single machine. In this sense, I would like to say that this is the right time to evolve from the single machine error to the multi-machine error. We propose DEX to enlighten this multi-machine error. DEX is short for Distributed Thread Execution Environment and started as a part of Popcorn Linux project. Currently, processes are bounded in the single machine boundary as shown in this figure. Popcorn Linux is to break the wall between machines and to allow the processes to span the execution boundary over multiple machines based on different ISAs. To realize this idea, we split the project into two parts, which are DEX and Popcorn Compiler. DEX, previously called Popcorn Kernel, takes the role of extending the execution boundaries, whereas Popcorn Kernel handles the challenges in running application on heterogeneous IS environment. To extend the execution boundary, we want to make it happen in a simple and intuitive way rather than introduce complicated mechanisms that are hard to understand and hard to apply. DEX enables this by allowing threads to be migrated or relocated to any node at any time. When threads are running on different nodes distributed, DEX provides the consistent memory view to them with the sequential memory consistency. This brings many advantages. First, DEX supports the memory and programming model as is for existing applications. So we don't need to declare or change code to access shared data. Second, DEX fully supports the native thread synchronization primitives, such as glibc thread object and functions and Linux Putex. Thus, threads running on different nodes can be synchronized just like running on the same node. This makes it easy to apply DEX to existing applications. So let me show an example for that. DEX, we can migrate a thread to any node just by calling this migrating function. In this example, the OpenMP will make 6 threads in here, and each of them will process a part of this array. If we want to run 2 threads per each node, we can just insert these 2 lines there, and then DEX will migrate thread 2 and 3 to node 1, and 4 and 5 to node 2, and that's it. So as you can see, DEX is very simple to use and provide a very intuitive way to scale application performance. To estimate the simplicity, I asked one of my PhD students in our research group to apply DEX for these 8 applications. The student did not have any background on those applications. However, he could apply DEX by simply analyzing the structure of the application where these threads are spawned and divert their execution. For the student, it took only 3 days to convert all those applications, and most of the changes were just adding these migrating function in there. When we run an application with DEX, its state will be like this. From the point of the application, it looks like it's running on a single node. But under the hood, the threads are spread on different machines and running on them in a distributed way. DEX provides a consistent memory view to those distributed threads by transporting memory data between the nodes. In the following, I will explain how we implement this migration and transporting data and its challenges to realize the idea. First, DEX should migrate execution across machine boundary. To implement this feature, we leverage the machine mechanism to perform the context switch in the operating system. At the origin, where the process was first created, DEX collects the execution context of the calling thread. It is actually stored during the system call entry for the migration. This execution context is transferred to the remote node and injected to a newly created process. Now, we can replicate the execution context across the multiple machine boundary. There are 2 challenges to migrate execution remotely. The first one is to handle call save registers and floating point registers. These registers are not automatically saved during the system call entry. So we build a user level runtime to collect those register values during the migration and restore them on the remote node before resuming execution of the original source code. The second challenge is to handle frequent migration. We observe that many applications iterate to create, migrate, and terminate threads repeatedly. To optimize this pattern, we create a process at the remote and use it as the template to fork remote thread for that process. Also, even if all threads have left our remote node, DEX keeps the memory data until the process is finally finished. Because DEX can reuse those data when a thread is migrated back to the node again. The next feature to explain is to provide the consistent memory view to distributed threads. Essentially, we implement the distributed shared memory system that performs the traditional read replicate and write invalidate protocol at the page granularity. Note that it is implemented in the virtual memory system in the Linux kernel, so it is done fully transparently to the applications. So in the beginning, the origin node, where the process was firstly created, owned all the pages for the process. And the origin actually controls and tracks the ownership and the location of the up-to-date data for each page. As we migrate the thread to a remote node, it will read the page for data. In this case, it contacts the origin to get the ownership and the data for the page. The origin examines the request and finds the up-to-date data for the request and responds to the request accordingly. To implement the write invalidate protocol, the origin can invoke the ownership from the nodes that own the page. The most challenging part to implement this feature is to tame the inheritance concurrency in the page port handling. Since the page port handling is on the performance critical path on the operating system, Linux handles the page ports in an optimistic and a concurrent way. So this approach can accelerate the page port handling. But however, it can read concurrently handled page ports to be rolled back later, and it actually complicates our DSM design and implementation significantly. So please see the paper for the details of that scenario. To efficiently handle concurrent page ports without causing the rollback, we employ the reader-follow model in the page port handling. The reader is the first thread that triggers a page port for the page at a moment. It actually processes the page port by bringing the page data from remotes, fixing up the page table, flush the TLB if need, and so on. On the other hand, the follower is the thread that triggers a page port for the page that a reader is working on. The reader can utilize the reader's result, so it waits for the completion of the reader's page port handling rather than blindly initiate a concurrent page port handling. So by doing this way, we can eliminate the rollback in the page port handling and make our DSM system more simple. The next challenge for the consistent memory view is to synchronize VMAs. So VMA stands for Virtual Memory Area, is a contiguous memory region with specific properties, and thread should have the consistent VMA information as well as the page data. However, VMAs can be frequently manipulated by malloc, free, loading shared library, and synchronizing the VMA information for each of these operations can incur a high overhead. So we employ raised VMA synchronization in DEX. The idea is threads tend to have localized VMA accesses, and node can keep the VMA information in an on-demand manner. So all VMA operations are forwarded to the origin and perform that data. For the VMA operations that expand the VMA range or give more permission to VMA, the result is only returned to the node that initiated the VMA operation. Other nodes can get the updated VMA only when it accesses the updated VMA. However, for the operation that shrink the VMA or remove some permission, the result will be broadcasted to all nodes to prevent illegal access to the unmapped VMA. Now that the application can run on multiple nodes on DEX, it actually runs on different OS operating system instances. This implies DEX should have some mechanism to provide the distributed thread with consistent kernel feature across machine. But practically, it is infeasible to re-implement every kernel feature in a distributed way because of its high engineering effort. So DEX actually employs the work delegation pattern to resolve this issue. When a thread is migrated to the remote node, the original thread is put to sleep. And it will be run on the remote context. When the remote thread call a system call, its arguments are forwarded to the sleeping thread in the origin, and the system call is processed in the context of the original thread. The result is forwarded to the remote thread like this way. And after sending the result, this original thread will be put into sleep again, waiting for the next system call request. This way, we can systematically implement many kernel features with a wrapping layer. The DSM in the DEX operates at the page granularity. So if some data on a page is referenced by different nodes, it can cause a false page sharing and degrade the system performance significantly. To remedy the page fault sharing, we made a behavior analysis tool to identify false page sharing. We can run DEX in a profile mode and collect page fault events. And the tool analyzes the event and points to the location that can cause the page fault sharing. This process is very simple. So to verify its simplicity, I asked the PhD student again to try to optimize the initial implementation, the initial applying of the DEX to the application, and it took another 4 days to mitigate many page fault sharing. As you can see from this table, the optimization only modifies a small part of the original application, and it took, and we believe this suggests that DEX is very practical and easy to use. So we implemented DEX on the Linux kernel 4.4, and it took around 10,000 of lines. Currently, DEX is working on x86 and ARM and support both InfiniBand and Ethernet network. The source code is available in the GitHub with the README file containing the procedure to test it. So please check it out from the GitHub repository at this address. So we evaluated DEX with 8 applications. grep and k-means are in-house application. BT, EP, and FT are from MPB benchmark. Black scores are from the Parsec. BFS and BP are from Polymer, which is a graph analytics program. We measure the performance of application on a single node with 8 threads, and we report the normalized performance while increasing the number of nodes from 1 to 8. Each node can provide 8 cores in the evaluation. So 8 node configuration will run the application with 64 threads. This initial result implies the performance of the applications when the student converts those applications just by inserting the migrating function. You can see the result is somewhat disappointing. 5 out of 8 applications show even worse performance than a single node configuration. But surprisingly, these 3 applications scale its performance when you put more nodes in the evaluation. And we can convert those applications in a with a very few lines. So this implies that some applications are scale ready, and DEX allow them to utilize remote resources easily and efficiently so that their performance can scale on DEX. We attempt to remove the post-page sharing that caused this performance drop. And by using those analysis tools, we can optimize this application. And this comment shows the most effective optimization for the application. As you can see, these 2 applications, grab and k-means, are now scaled with the simple optimization. So specifically, we isolated post-thread IO buffers by aligning them to the page boundary. And it removed the majority of the post-page sharing and making this application to scale. The performance of BT is not very scale, even after optimization, but now it outperforms the single machine configuration. Now only 2 out of 8 applications does not have a performance gain from DEX, and this suggests that DEX can be very effective to many applications. So that's the end of my talk. So I presented the DEX, which is distributed thread execution environment. It allowed to easily migrate thread to remote node and provide a consistent memory view to distributed thread. And we provide a behavior analysis tool to reduce post-page sharing. And source code is available in here. So please feel free to access check the code. And thank you for taking your time for this presentation.